This is question 12 of the component 3 in-class question book for the lower 6. There are many reflex actions involving a sensory input to one side which results in a contraction of effector on the opposite side. Okay. Right, normally a reflex action in your reflex arc would be sensory neuron, connector neuron or relay neuron or intermediate neuron, and then motor neuron out the same side. On this one we're saying it's on the other side. So we've got receptor here, and we've got effector there. So the first thing we're going to have is that's our starting position, and this is our ending position. So we've got the left and the right side. Okay. Then second one is, can we remember which one of these has our sensory neuron in, and which one has our motor neuron in? Well, this dorsal root, you might have drawn it in class. So this is the dorsal, and this side is the ventral. So our sensory neurons would be in the dorsal. Okay, so let's start off. So we've got our receptor, and then we've got our neuron going here. We've got our cell body there. Then we would have a synapse there. Then we would normally have an intermediate neuron there. In this example, they're not too worried about how we draw this intermediate neuron. I'm just going to draw it kind of sort of that way. Okay, and then we've got our effector. So the motor neuron would go on the ventral side. So our motor neuron cell body will be like that shape, and then it's out there. So those are the directions anyway. So the cell bodies, the sensory cell bodies will be in the dorsal root ganglion there. The other two cell bodies are in the grey matter, that's what makes it grey. And then we've got our effector, that's having our muscle, that's moving our body weight, and so on. So where are the marks for that? The first mark is labelling our neurons. So sensory neuron. So label all the structures involved. So sensory neuron and our motor neuron. We have our synapses in the grey matter, that's the second mark there. Cell bodies in the right place, that's our third mark. And the positions of the sensory neuron on the dorsal side, on the receptor, and the ventral side on the right, our motor neuron. So that's where our 4 marks are. Wow, that was tricky. The higher sense of the brain can override a reflex action by using an inhibitory synapse. So you don't necessarily know a lot about inhibitory synapses, but they give you all the information here that you need to answer a question. The synapse results in the transport of chloride ions and potassium ions across the postsynaptic membrane. So what are we talking about? Here's our presynaptic membrane, and there's our postsynaptic membrane there. And they're telling us that we're getting chloride ions and potassium ions across the postsynaptic membrane. They're not saying which way. What would normally happen? Well, what would normally happen, we'd get our transmitter going across the synapse, so transmitter going across the synapse, and then we'd get sodium going in, and that would generate the action potential. So this is inhibitory. So how could we inhibit this? Well, this is all about thresholds. So we'd have to get enough depolarization to have a threshold here. So this is going to start off at, say for example, minus 70 millivolts, and then our positives are going to come in and reduce that minus 70. Eventually it will be depolarized. So how can we muck this up? Well, if we move chloride ions in, so if we moved, say, chloride ions in, then that would go to maybe minus 80 millivolts perhaps. And so that means that we'd need more sodium to get our threshold. So that'd be one way of doing it. Or we could, if we moved our potassium ions out, I can't spell K, moved our potassium ions out, well, that would also make that minus number more minus, so it might turn our normal minus 70 to minus 80 by moving pluses out. And that would also make it harder for sodium to depolarize or generate an action potential. So we just need to put that into words there. That's pretty tricky, is that, for these 3 marks. In fact, this whole page is pretty rock hard, really. So chloride ions move in and potassium ions move out. Chloride ions move in, potassium ions move out. And so the resting potential is lowered, or the potential difference becomes more negative, for example, like that. So resting potential is lowered, e.g. from minus 70 to minus 80 millivolts. Just as sort of a little example to show that you know. It might be more than that, who knows. So that potential difference is, or you see that the potential difference is bigger, another way of saying that. And so the threshold requires more depolarization, so you can have more depolarization of sodium coming across to have an action potential. So threshold requires more depolarization for an action potential. So that's proper biology, that. Pretty good. Let's hope it gets better, this question. An experiment was carried out to investigate distance travelled by a non-myelinated neuron following the application of strong stimulus. Okay, so distance over time. Okay, calculate the speed, distance over time. So speed equals distance over time. Bit of physics. Distance 2.5 millimeters. Time 5.7 milliseconds. Are those the units? Yeah, millimeters per. Yeah, okay. So 2.5 divided by 5.7 is that number there. 0.43859664. Give your answer to 3 significant figures. Show your working. Well, we've shown our working. 3 significant figures. So it's that 4, that 3 and the 8. We've got a 5 after it. So 3 significant figures. Depends on how you interpret this, but you could say 0 point being one significant figure there. So you can have that there, so 0.44. Or if you're arguing that your 3 significant figures are after that, then that'd be 4, 3, 9. The mark scheme wants 0.44, and saying this 0, this point is significant. D. In this experiment, the value of the action potential was all the same at all distances tested from the stimulus. Describe and explain how the action potential was generated in the neuron above. So how is an action potential generated? Right, we're back on familiar territory there. So how do we go from resting potential to action potential? Just cut and paste your notes into this now. Okay, so sodium channels open and sodium ions diffuse rapidly into the axon, and that happens by diffusion or facilitated diffusion. Because it's through a channel. Then we've got 4 marks here, so we're going to have to do a little bit more. Let's talk about other channels that we've got. So K plus channels remain closed, and then we've got why have we got an action potential? So we've got more positive ions inside the axon than outside. So we got it's plus 35 or 40 millivolts, and so we get depolarization. Of the axon membrane. And that will lead to the action potential. So we just try and split this into four chunks. And the last couple of marks, explain why the value for the action potential was the same at all distances. So this is an action potential. It's like shooting a gun. If you pull the trigger lightly and it goes off, or you pull the trigger medium, it goes off. If you pull the trigger hard, it goes off. But the speed of the bullet, will be exactly the same. So it's the kind of all or nothing response, or nothing response. Now, once you've reached that threshold, the same size action potential is generated. So the action potential will be the same. It's either there or it isn't. Once that threshold potential is reached. So once the threshold potential is reached, the same size action potential is generated. I'm just describing that all or nothing response. So if you got 16 out of that, 16, you're a brilliant biologist. If you got 10, then that's probably alright as well.